Our next speaker, new to the conference, Dr. Reed Mosher, who is the Director of Information Technology Laboratory at the U.S. Army Corps of Engineers, the Engineering Research and Development Center, URTIC. Please join me in welcoming Reed Mosher.
Thanks, Mike. Can you all hear me back there? All right, very good. I appreciate the folks running the conference to kind of adjust schedules. We had a plane canceled last night, and first time, I fly a lot, like a 2 million miler on Delta, that they couldn't start the engines. They didn't have any devices to start the engine, and they had to go borrow from another airline company. So that was kind of a first for me this morning. I'd like to talk about, we are one of the DoD high-performance computing facilities, and how we use supercomputing in our computational engineering to help us in our engineering tasks, okay, and how it's become a mainstay of how we do things. The role S&T and DoD is to provide state-of-the-art science and technology to keep us ahead of our adversaries. And that has been the mission for S&T and DoD since its inception. And part of that is creating the necessary, or really doing revolutionary warfighting types of capabilities. And it shows some of the first down there at the bottom, internet, mass production, jet engines, those types of capability that come from DoD science and technology. But our high-performance computing is broken down into these computational areas. We call them computational technology areas. And these are the main bins that we put our science that's related to computations into. One of the things we have to be aware of is, why does DoD, pursue this supercomputing capability? We try to stay, when buying supercomputers, we try to stay in each one we buy, a major machine, in the top 25 out of the top 500 machines to try to keep at that cutting edge. You can see in 1993, if you look across the world, the U.S. was one of the largest in dominating in supercomputer capabilities. And if you see now in 2010 that it's really expanded. A lot of different countries have decided that there's a strategic part of their interest to have supercomputing, both in the military side of things, but also in the industrial side of the world. Some of the more recent headlines is, the investment that Europe is making. The Russians have moved into making it a top priority. South Korea. China has been a major player in this in the last 10 years. And then, the kind of question, well, where is India headed in this area? A little bit about URTIC. We are located, headquartered in Vicksburg, Mississippi. We have 4 laboratories there. The one I'm the director of is located there. We also have one in Alexandria, Topographic Engineering Center, another one co-located at the University of Illinois, and another one in the co-regions land in Hanover, New Hampshire. It's another little tribute is that we're a Corps of Engineers laboratory, but we do research for the Army. We get about 6% of the S&T budget for the Army, yet in the last 3 years we've won the Laboratory of the Year, and over the last 12 years we've won it 7 times. So for the small amount of money we have a significant impact on R&D for the Army. So we have some unique facilities. One of those is our High Performance Computing Center. We have some information facilities, compartmentalized, centralized, sensitive activities. Our co-regions has an ICE engineering facility. We have one of the only licensed hazard and toxic waste centers. And we have we also do a lot of hydraulic modeling on what we call the civil works side, locks, dams, navigation, that type of work. Funding first, we're about a $1.2 billion funding authority for our work. Most of it is Armed Forces support, about 70%, and most of that is reimbursable, meaning that we do work for others. It's not part of a actual budget. And then we have about so 20% at Civil Works, and Civil Works also includes the work we do for the Department of Homeland Security, EPA, and others. Our areas that we break down into Warfighter Support, dealing with mobility, terrorist threat protection, force protection, hard target defeat. We do work in the military installations, dealing with installation operations, sustaining and also on construction rehab. And then we have a Civil Works mission which deals with water resources, navigation, flood control, environmental, regional watershed solutions. And we do quite a bit of work on security of dams and other facilities for Homeland Security. This is a typical use for last year of our projects, about 52 million supercomputing hours, and gives an idea of the types of work that we use our supercomputing capability for. Typically, they deal with incompressible flow, mass transport, compressible flow and structural response. We do a lot of weapons effects and air blast, and then some classic quantum and classic particular mechanics problems. Right now we're doing a lot in the materials development on molecular dynamics. So I'm going to go through some of the types of problems that we have solved using supercomputing and give you an idea of the impact or how they are actually used to support the warfighter and others. This one is dealing with sensors and when to use sensors, particularly for IEDs. In the past, sensor developers would do a lot of field work where they would hide something out in the ground, try to find it. And so we actually took a different approach where we went at it by trying to understand what was in the haystack as opposed to what the needle looked like in the haystack. So we did detailed analysis of the soil, the response due to heating, the electromagnetic signature that you get from the soil, and the changes due to evaporation, sunlight causing evaporation, and try to find and define an electromagnetic signal sense numerically, how you could determine what was taking place when you disturb the soil. And some of the things the process that we used for doing that had to do with both experimental and a computational standpoint to create a virtual test bed that people could use their sensors against virtually before they went out in the field to see how well they worked. Now this even got into detailing how you describe plants in electromagnetic sense, and also their projection and geometry on the ground, how they create shading, even to the point of looking at how the fluid flow goes up a tree during the day and back out, and how that affects the ground underneath it. So, and what it has done is created the ability to decrease the number of false alarms. False alarms used to range in the 40 to 60%, where we've been able to get these down to being above 90% for false alarms. So they have a much greater ability to determine that if you've got something there that's really going to be there if the processor delivers that. And what we can do with that, we can actually tell people when they run the sensors looking for IEDs what time of day should they run them, when are they going to be the most effective, and kind of altitudes and other things that they ought to be flying those at. This is a typical result. You can show on a 24-hour clock when's the best times to be able to use it, and when you're most likely going to be able to see something in a given scenario. One of the other areas where we're using molecular modeling, we want to be able to try to understand at scale why different materials behave as they do. We model a lot of things at the finite element level. We're modeling things to failure, particularly in blast events. But what actually controls it is either at the microscale or nanoscale level or even below that. So we're doing a lot of work to try to determine what is the controlling factors and can we actually design materials, add things to them at that level to get better material performance. Particularly looking at carbon nanotubes, carbon materials, and how we can actually do chemical bonding between the different materials that the carbon is mixed with. A piece of that is not only just the creating the material from analysis standpoint, but also figuring how you actually manufacture those materials, how you can actually synthesize that material. And so a large part of our computations go into how you can actually create those, and then our synthesizers in the laboratory can use that to help create those materials to get the performance that we're looking for. Now, a lot of this is being done at small scale, and eventually will lead up to being at the full scale level of actually manufacturing materials. One of the other areas that we're is supporting our troops, particularly protecting them due to rockets and mortars. It's generally called overhead cover. In Iraq and Afghanistan, we have eating facilities, places where people gather, and we're concerned about being hit by a rocket or a mortar, and how can you protect our folks from that. So we've done a number of things, and those have involved high performance computing used with experimentation. And most of our things that we have a strong experimental program that also supports the computation part. So the computations may not necessarily reduce the number of tests that we do or the testing part of it, or eliminate it. What it does is that we actually have a better product to start with. So we may do less testing, or we can do faster, more tests at a time to get product to delivery for the folks. This is an example of a mortar coming in to overhead cover. There's a burster slab to create it to go off, and then protection below it. And we also have computations that support also that. So the computations help us in actually not only understanding what takes place, but also on when it comes to designing the framing necessary to support that. This is a lightweight protection system that can be deployed by soldiers, essentially to replace the HESCO bastions filled with sand. It uses fiberglass and specially designed concrete panels. Protection against near rockets and mortar detonation. And with a screen on the system, it can actually use to stop an RPG. And that can all be, you can assemble this with 4 soldiers. You can pack on a back of a trailer to a Humvee or another vehicle to be used for temporary setup, taken down. It's called a modular protection system. I hope this one works. And this is just an example how we use Dyna. We had a problem with actually the top rails flying off when they were hit with a blast. And we were able to correct that and make some changes to the system through our Dyna model. So essentially they were peeling back, and we were able to make a change to the configuration so that wouldn't happen in the future. And here's the results of that. And the difficulty here is that you're not just stopping the blast, you're actually stopping fragments that may be going between 4,000 and 6,000 feet per second. This is a situation I actually have, hopefully have turned the sound off on this. That's a IED going off in a culvert underneath a road in Afghanistan. Those guys didn't say gee whiz when it happened. And what we've been working on is ways to not only detect them, but also to strengthen the road surface in the culverts so that we can't really, the blasts, they can put so much explosive in there we can't stop from causing some damage, but we can reduce the injuries to the soldiers if it goes off so that they're not, you don't have as much impact in shock effects to it. And then we've also worked on ways to keep people from getting into culverts, so they're harder to get to. A big portion of all that's been done here of initially looking at involved high-performance computing, supercomputing calculations to help determine what took place. This is a situation where a soldier needs to get through a wall to rescue or to get into an area on the other side, and it's called breaching. Typically how it has to be done is you set explosives against the wall, blow a hole in the wall, blow a hole in the wall, and then the soldier has to go up with his rifle and actually hook onto the rebar and cut it open. And so they're working on developing a technique where you can actually remove the concrete and the rebar without having to expose the soldier in front of the hole again. It needs to be 39 inches so he can get through it with his pack. And this is one of the examples that was used. I actually can't show you the one that's actually came about because it is sensitive, but the one that actually came about was determined how to place the explosives and everything calculationally before they ever went out in the field to do it. And then they went out in the field and proved it would work. So the arrangement, so it wasn't a trial and error, it was done by computations first before we went out to do that process. And it seems to be acting up a little bit, but the key was to be able to, the explosives is really good at moving the concrete, but its difficulty is moving the steel. One of the other concern about IEDs, particularly as the damage they do to our injuries to our soldiers and our vehicles. One of the difficulties in experimentally, they weren't able to actually recreate experiments that were repeatable every time. And when they came to see us about it, the folks at TARDIC, we talked to them about the fact that if you change the soil conditions, you actually change the amount of force that's being departed to the vehicle. And so you have to actually include in it the soil particles as part of your loading and be able to figure out, depending on their density and that part of it, what will be the actual loads departed to. So we were able to, create a model where we could actually, hopefully, hang on. All right, here we go. A model where we could actually take into account the actual soil particles that would be generated, against the bottom of a vehicle. Now, this has been so successful that there is actually going to be an institute looking at vehicle response, so they can to do the numerical modeling, so that you can actually determine what are the loads to the soldier that's actually sitting in the driver's seat or in a passenger in it, so that we can determine what needs to be done for future vehicles to reduce that load on the soldier from a IED. One of the interests of air-delivered weapons is to, if you're guided weapons, can you go after a bridge, and what do you need to take down a bridge, and what is the targeting for that? And so, through calculational methods, we've been able to determine, what would be the fusing and what targets to go after the bridge if you want to take it down. And this is actually rolled up into an easy calculational method, engineering calculation method, to provide that to the targeteers. One of the other areas is in critical infrastructure, particularly the work that we're doing for the Corps of Engineers and Homeland Security. We've looked at many of the major bridges and new construction. Particularly bridges are very vulnerable because a lot of their supports, you can drive a truck up beside them. Other areas of concern are tunnels, where our tunnels are located, particularly subway tunnels. Concerns, how can we take a lot of these older tunnels that were built turn of the century, early 20s, and can they be upgraded for protection in the future? This is also an interest that the UK has. We've been working with the UK on some of this. And then particularly with dams and earthen dams, concrete dams, major high head dams such as the Bureau and the Corps has both about 500 to 600 dams each, and concerns about those dams as if they were attacked, what kind of problems could they cause due to flooding, and how can you protect them? What kind of standoff distances do you need to provide? And actually created, from the high performance computing and the experimental work, some engineering level tools. It's called AT Planner for Dams, to help in doing those assessments. We've also been involved in a number of dealing with disaster response, from Hurricane Katrina modeling of what happened in New Orleans to what took place during the oil spill here this past summer, particularly with along the Gulf Coast, helping with FEMA to determine their maps for the 100-year flood area, creating a risk model with running a number of different scenarios of tracks of hurricanes along the Gulf Coast, and being able to create a distribution of what the surges and waves would be for that scenario, and that will lead to where the flood levels for the hurricane maps that FEMA distributes now. For the oil spill, the governor of Louisiana wanted to block off a number of islands in the Caernarvon Division Pass. We were able to actually take the models that we actually did for the hurricanes to run analysis against them and show that if they actually had filled in between the islands, it would have actually made it worse. By actually having the openings between the islands, that allowed the oil to be flushed back out. Otherwise, it would have gone in there and stayed stagnant during that time. So, you're able to take some innovative idea that the people are trying then to show whether it would actually work or not work was one of our activities. Now, move on. I know, try to stay on schedule here. I need to move on a little bit. Let me skip this one. We're working on a whole range of hydraulic and hydrology models so that we can assess the full basins, say the Mississippi Basin, the Ohio Basin, and to do that modeling from both the hydraulic and the environmental side. That's one of our efforts, to get better predictions of what will happen if a water conditions, high floods, those types of problems. One of the more interesting ones was also the vegetation of levees. Here was a concern, particularly in California or other places where you had trees growing on the levees, and using the numerical modeling, can we see what would be the effect of those trees? Does it affect the stability? Does it affect the seepage conditions? And using high-performance computing to help and make that assessment, along with experimental work. One of the other areas is net zero. There is a plan to have net zero energy for our installations. To a large part, that's going to deal with conservation, and can we do modeling across our installations to understand what is the load for cooling, other types of problems that we run into for our installations, and help to make decisions whether to replace buildings or to use more insulation, more glazing to reduce the energy draw. Just a couple things about the future. Some of the things that we see, a lot of the work that people are using for codes are homegrown codes or very specialized codes. Very little of it is reusable type software. We have a lot of inefficiency in our I/O capability. And our connection between what we do on the desktop and our HP is the slowness between those, and our connection between those is a concern, a limit for our productivity. Big is, we're getting much more power, and with extra scale probably coming in the future. Does that mean that we will actually have that capability to do our calculations? This is a little, currently this is well, not actually our biggest machine, but we have new ones since then. The folks at Oak Ridge have one that's 10 times bigger than that. We know that the future will even be more times that. Software issues, expanding expression of our parallel work today for execution. We're going to have to figure out how we can actually take advantage of all the processes that are going to be available to us. And right now our software, we're having to hand do a lot of the programming to get to that point in our current systems. How are we going to do that when we have hundreds of thousands of processes? And to take advantage of it, we're going to need that capability. So programmers will have to handle massive concurrency. The reliability of the components, we're going to have processes that will have much greater fault occurrences. And we need to be able to keep on calculating our problems, even if we do have problems with reliability. And the science is going to take us in another direction. We're going to go to even greater detail in the science at a lower scale, and we're going to need to be able to branch between scales. So the horsepower that we're going to get in supercomputing is going to greatly enhance what we can do in the future. Some of the examples right here is being able to go from the quantum mechanics scale all the way up to the continuum scale. We have both time and size scales that we have to worry about. One of our examples is with some of the materials, concrete, other types of materials on that in the construction industry. They are they're not a homogeneous material. They're a heterogeneous material, and we need to understand if we're going to be able to add things to those materials to make them stronger, increase their strengths by 10 to 100 times, we have to understand what's taking place at the nanoscale and the microscale level in order to achieve those potential increases in strength in use of those materials. With that, I'm try to keep on schedule. I appreciate you inviting me to come talk. Got a little time for any questions if there are.